So, today we are going to discuss how the land use land cover modeling can be done using different machine learning and as well as statistical based techniques. So we'll just go through that one of the specific models and then one and two case studies that how it's being used for different modeling purposes. So let's first understand that why do we need to study the land use land cover changes. So it's basically the land use land cover is going to have an impact on environment as well as the quality of life on human beings. For example, let's say in a city, one of the important aspect which in nowadays people are realizing it that there has to be enough green space available to per capita people who are living there, because that on the basis of that you're going to have specific park and the corresponding areas for the park and other areas also needs to be provided. So it's a kind of the quality of life is also dependent upon the land use land cover changes. Then of course there is an habitat changes happens. So if there is an change in any biodiversity areas, like if the water is getting clogged or if there is a loss of let's say wetland in a city, then it has an impact on the overall health of the cities. Same way is also the case for the water qualities and other quality of life. So all of them are dependent upon that what is the and all of them has somehow linked to the corresponding land use land cover changes. So we need to do a study for land use land cover cases, and nowadays we are also seeing a large impact of these changes are related to air quality in a particular city environment and in surrounding areas as well. So I'm just going to talk about one of the specific models which was built as a part of IGBP LULC projects. So it was a part of the ISRO's, and outcome of that is one of the models which has been generated. So total overall research objective was or basically was of the project was that we had to look for decadal changes. So where are the changes which has happened in 85, 95, 2005. So 3 decades different changes happened, especially in the cases of whole India, and then what is the corresponding impact on different hydrological regime. So that's what the basic objective and that's what the basic research questions which we started with. And then we collected a lot of socioeconomic data sets, and based on those socioeconomic data sets we should be able to predict that how the future will look like. So any kind of modeling requirement is the case to peep in and provide some kind of indicator what is going to happen in futures. So that was the one of the objectives. And then we are also able to study and find out what are the different hydrological impact of those land use land cover, especially in the hydrological regime. So that was the final objective of the projects. So we can find out the detail of these projects there's already published data sets on the basis of all these objectives, which was published in 4-year backs, and it is available openly in an open domain. So let's see that how do we, if we want to do some kind of modeling processes, so we need to understand that how the things is going to work. So if we are looking for a kind of land use land cover changes, then we need to understand that how the state of a particular piece of land is going to change in a 2 time period. So that's how we can basically create a model which will say that one particular land use is going to remain same as which was previously. So that is, it is the land use 1 was already there and it will remain in the land use 1 state. So it means like a piece of agriculture land, even after 5 years or 6 years, it will remain the piece of agriculture land. So there has not been any activity. At the same time, there may also be a possibility that that particular piece of agricultural land may get converted into some kind of built up land and so on. So that's basically the another possibility is there. So we have to look for that why is it that one particular piece of land is going to get converted into another piece of land. So that's, or it is remaining in that case. So that is going to be governed by the land use or the land cover characteristic itself. So it means like if, for example, let's say if the built up area is there, so it most likely for next 5 years, 10 years, or 15 years, that particular piece of land remain into that. So it means like it has some kind of resilience associated with that, and it will remain into that state. So this is called a survivor rule, or it tells that it is very fit, or the land use is fit for a particular piece of land. It will remain in that case. Then there is also a possibility that if the agriculture land is getting converted into some commercial or built up areas, so that's, we call it a death rule. So that death rule, that earlier land use cover 1 was there, it got changed into land use cover 2. So these two rules can be governed by various type of suitability maps, or the basically suitability maps are nothing but it tells you that a piece of land is good for what purposes. So we can create a kind of probabilistic distribution of that data sets, and that can be considered as an there might be some threshold or some interactions of those probabilities, which we can use it for giving the rules for either the piece of land will remain same or it will change. Most of the time what happens is that these play or interplay of these land use gets governed by certain socio-economic drivers. Like for example, if the new airport comes, so suddenly there will be development, and a lot of agricultural land is going to get converted into basically the different type of built up areas, and the cost of the land will also go up. So in this case, there's a two factor which is involved. One is called the human decisions. So as a government or policy managers, we had decided, or somebody has decided, that there has to be a larger airport has to come, or maybe a larger commercial areas has to be built, or a certain economic zone has to be built at a particular places. So those human decisions, along with the socio-economic drivers, is going to influence the survival and death rule of these classes. So generally whenever we say socio-economic drivers, so we are mostly related to the kind of land, its property, or then corresponding population densities, and then the different type of, especially if you're looking for cases like agriculture and forest or soil productivity, and other characteristic also plays an important role. So we can derive a metric which will combine these different drivers to provide a suitability of a particular land use maps. So this is just an overview of in any kind of land use land cover modeling which we use it. So one of the modeling framework is OpenLDM, which is available in publicly domain, and anyone of you would like to use it, they can use it. And if there's also a possibility of making some modifications and contributions to these projects. So if you look into these frameworks, so there will be a certain drivers at time t1. So those are actually on the top, which you can see. That's basically the land use cover at time period t1 and corresponding drivers, which is available at t1. These two, so each of these driver will have some kind of influence on a particular land use land cover. So accordingly we create a models. So for creation of these models, we can use various type of techniques. So some of them may be a statistical based techniques. We can also use machine learning based techniques. Random forest can be used, SVMs can be used. The basic objective of those techniques are just to establish and tell that what is the impact of different drivers on a particular land use. So that's what we are going to derive it as a part of model fitting, and these models can be of maybe a statistical base, or it can also be a kind of machine learning base. And once this model is getting created, then what we do, we look for a kind of different drivers, and we see the significance of those drivers, and we take a decisions that a particular land use should be, shall we say that the driver impact of a particular driver is good enough or good enough on a particular land use. Mostly in the statistical term we use a p-value for that. So if the significance p-values is good enough, then we select that particular driver of a land use. For example, let's say if I talk about in a particular area, you may be having a built up, then there may be a commercial place, a commercial area, or there may be a residential areas and so on. So commercial area will have a lot of impact on what is the distance from the city centers and so on, where the residential area will have drivers like what is the road density at a particular area or zone. So those kind of drivers can be there. So both of them, the distance to road and the distance to commercial hub center will play different roles, or in other words, will have different weightage of influence on residential and as well as commercial areas. So we see those impact, and then we go ahead and we say that one particular driver should be included and not included. And when we do that, then we can do a fitting of models. So there can be a multiple parametric and non-parametric techniques like ANN and random forest can be used, or we can also use parametric techniques like regression analysis and so on. So once we have established the relationship, that's called a model fitting stage. After that, what we do a reweighting of each piece of land based on the conditions, that is the particular class or land use class has an influence of neighbors or not. So what has been observed, like some of the land use, for example, built up area will have a great impact or influence on the basis that what are the other built up areas, or how much areas around a particular piece of land is already converted into built up. So if the piece of land is, if the fraction of land in surrounding area has reached, let's say 40-50%, then the conversion rate of remaining lands can be very fast. So these kinds, it means like there is a kind of influence of neighboring neighbors in this case. So on the basis of that, we can reweight the land use maps, and that's what we do it as a part of suitability map with weighted suitability map generations. So once this suitability map is generated, which also indirectly says that what is the survival capability of each of the land use. So that particular thing will be available as a part of suitability map. And then based on the demand, like whatever changes might have happened in the future, what is the expected demand, we do our demand allocations based on the suitability map, and then we generate the output. So these demands can be generated one shot, like for example, if we are taking input data for 2000 on 2500, or maybe 2015 on 2020, then in one shot we can also predict that what will be the land use, land cover changes which we expect in 2025. So in between we can also generate some kind of intermediary inputs. So as a part of the models, there's also a possibility to change the allocation rates, or the amount of land cover which will get changed. So these changes can be a part of some kind of policy decisions. For example, let's say if government decides that the urbanization rate which was there earlier, that has to be doubled in next 5 years. So it means like the conversion rate of any agriculture land or any kind of land which was getting converted into an urban or built up areas, the rate of that conversion will be doubled. So it means like there will be demand, additional demand, and accordingly it is going to have some kind of impact. So that's what we can include it as a part of future demand generations. In some cases there might be some policy restrictions that you cannot do a conversion from one land to the another land. For example, there may be a reserve forest, so there is no possibility of changing the reserve forest areas into some other cases. So those kind of areas or the conversion can, or the class migration restrictions can be put in, or in some cases we can also say that in which order a land should be used. For example, let's say a piece of land is there and it is good enough to build a house and as well as hotel both. So in that case, we can prioritize that if such a scenarios arises and if both of them are having almost equal probability of getting development, then we should give a precedence to one of these class. So either we can say that if there is a clash of suitability or the strength of a land use at a particular piece of land for two different classes of same type, then in that case we can say that the first one should take precedence. So that's also the class migration or the conversion order is there. So these are the specific policy decisions which can be put in as a part of model and then can give you the output. So we'll see a few examples of that in the current cases. Before that, we just see that we are going to look into a small representations that how these things gets put in form of let's say a mathematical relationship. So suitability maps can be generated based on for each land use cover map we can have different drivers, and those drivers will have some kind of weights. So those weights can be derived statistically or with the base of machine learning, or it can also be derived on the basis of individual choices. So that is going to give the land cover map. So in the logistic models or a linear or maybe a neural network based models, those coefficients get generated under certain constraints, and then the weighted suitability map generally happens by taking consideration of what should be the aerial distances or influence. So if the one piece of land will have only impact on its neighboring areas of a unit distance, or it's a 2 times of that distance and so on. So that accordingly the weight has to be generated. So that's the we call a cellular automata based models, which gives the additional or re-weighting of whatever suitability maps which would have generated in earlier stages. Then there's an optimizations algorithm which works on the basis of allocations and the constraint of different demands. So this is basically overall summarized mathematical models which is used in any kind of land use model. So the models which you talked about, OpenLDM is there, that it is having different type of algorithms to establish the relationship between drivers and corresponding land covers. So those are the list of those, and it is also having a certain scenario generations, especially based on the different user demands and so on. And then we are also having a different mode of executions, and as well as there's also an accuracy assessment module. So this accuracy assessment module not only includes the kappa accuracy based measurement, but there are also another kappa indices which should be used for land use land cover changes, because the kappa based metric is not considered good for doing evaluation of land use land cover changes. So in those cases we look for some other indices. So those are also part of the models is available. So this is just an example or snapshot of the distribution of that data sets. So let's see an example that how we can use a simple OpenLDM cases for doing the activities. So in this case, what we do is we take a set of input data sets. This is the first screen which you will see it, and then we provide the date, the first time period and second time period data sets, and then we get the output map which will get generated. So that's how it's being put in as a part of the input on a data preparation stage. Once you have provided this input, then you have a way to select the different drivers, like what are the different drivers which particular land use land cover map or the particular land use going to have some impact. So like in this cases we are using 4 different drivers, and these drivers can be selected, and there will be established relationship between these drivers and corresponding land use land cover maps using different model fitting. So in this case we can use a logistic regressions or a neural network based or any kind of other statistical relationship which we think is good for a particular land use, and to establish the relationship between land use and drivers, that can be taken. So once you have taken these input, then it establishes the relationship which we can do a kind of evaluation. So those coefficients, whatever you see, is actually an outcome of the model selection. So if you use a parametric based model selection, then those coefficients will get generated according to that model constraints. So for example, like in this case, the built up will have an impact of basically distance to stream. So it means like it is having a negative relationship. So as the distance to stream increases, the built up area is also going to or the density of the built up areas, or the areas which is near to the stream is actually is not present. So that kind of relationship can be built in. So there are also other cases, like as the distance increases from the urban centers or the cases, then the built up area density is also going to come down. And in this case, we are seeing that the earlier urban centers which might already be there, so that has a more influence compared to any other driver. So you can build. So what happens is, as a part of modeling relationship, these relationships can be built in. So this is basically a case of logistic based analysis techniques. So same way we can use it for neural network based and so on. So once we have established and thought of, yeah, this is a good enough weightage which has been built by the or which has been established based on the basic assumptions of machine learning or maybe statistical analysis, then we can start applying the few of the policy decisions. So one of the policy decision which we had seen earlier is a kind of migration order. So you want to say the class 1, which is of type built up, are you allowing that particular built up to get converted into some other class or not? So if you allow it, that means like from the policy decision that can be taken. So whenever any previous state conversion is not there, and if you want to change that order, then always you have to think that there will be a kind of cost associated with that. For example, let's say a built up conversions to agriculture, it cannot happen naturally. There has to be an additional cost, and somebody has to bear the cost of that conversions. Otherwise, what we can do is we can take the way the business as usual, or the way the earlier conversion rate was there, so it should continue in that case. So in that case, most likely the agriculture land will get converted into built up, but reverse may not be possible. So these kind of constraint can be put, and once you have substituted that, then we can select for future predictions. So this is the next level of prediction. So once we have established the relationship in the earlier time period, then we would like to know what is going to happen in the future. So for that, considering the same kind of relationship existing between land use, land cover and different drivers, then we'll provide the corresponding drivers input, and that is going to give the output in the future. So that's what we are doing it in this case, that we are providing the output, and corresponding there are few also policy inclusions, like you want to modify the demand. So means whatever the earlier change of conversion of one piece of the land into another was there, so do you want to continue with the same, or there has to be some doubling or some reassessment of that is there. So we can put those additional demand in terms of number of pixel or in areas that we can put it. And then we can also say that how much of the earlier classes which is already built up or is already in a particular stage, what kind of percentage of these particular classes will remain in a particular state. So those are basically a class inertia, we call it, and that can be provided. So let's say if in this case we are using a built up is having a class inertia 1, so it means like there's no possibility of any piece of earlier land of built up was there getting converted into any other class. So additional built up has to come from other classes. So that may be in agriculture or some other land use or land cover that has to come, which will get converted into a built up areas. Then we also enable the spatial context. So in this case, we haven't enabled it, so it means we are simply considering it that there is established relationship, and only a piece of land which is having a higher suitability will get a portion of the representations in a final allocation phase. So that we can generate that, and then we can do a small accuracy assessment. So this is a kappa based accuracy assessment at different confidence interval that can be done. So in this case, what we are doing is we are taking 85, 95, and we are also having a 2000 maps available with us. So using 95 drivers, we predict the 2005 output, and then we do a comparison just to assess that how well our model is actually working in the corresponding study area. So this particular results gives you that output. But in cases where you will be doing a predictions of the futures, then the future map may not be available. So in that case, the accuracy assessment may not be used. But for the backtracking or understanding that how well your accuracy has been in the earlier cases, so you can use it this accuracy assessment cases. This is just an example of the total land conversions and final prediction output, and then using different colors we can generate the output, and a very simple output has been provided. So there's also an additional I should say the help sections which we can look into that, and then we can get a more detail. So this is just an overview of the OpenLDM framework which is available. Now let's say that how we can use this for different cases. So this is just an example that we are having a 3 time period of snapshot of land use, land cover, especially at the level 3 we are having different maps. So what was the condition at 2001, 2007 and 2013. So all these maps has been generated using object-based segmentation techniques that has been applied at those the satellite from the satellite imagery which has been collected in 2005, 2007 and 2013. And based on the object-based classification techniques and few filtering mechanisms, the corresponding maps has been generated. So this is just a kind of examples where the machine learnings can help us to generate the input data sets to find out the LULC trends. Then we use a set of socioeconomic drivers, like in this case we are having population density or the distance to hospital, or those are the basically accessibility or services which is available to us, different roads and the schools, the elevation which is again an important aspect especially in the hilly region areas, and the existing built up zones and so on. So based on all these socioeconomic drivers and the LULC map which was generated earlier, we can create we can generate the future predicted map. So there's also especially in the city regions, the circle rate or the cost of land also is an important driver, so that can also be included along with the accessibility factor to different services. So if you use all these drivers, then what we can do is we can establish a relationship between the different basically the drivers and population densities, then literacy rate. So earlier this was the cases which was accessibility drivers, and the next one is basically a socioeconomic structures, or basically the literacy rate, how much the number of household in a particular wards and so on. So these two drivers can be combined together to establish a particular land use, land cover. So based on that, what we can do, we can create a different type of suitability map. So in this case, there are 4 different category of the land use which we are talking about. One is that commercial, non-commercial, low income and high income groups. So it's basically, we are also trying to understand that in this particular cities, which piece of land is considered to be good enough for a particular income group. And that's one of the important characteristic of any city, which tells that in a particular zone or area, how does the social structures gets created based on income group. So that is being shown in this case. So you'll see that in the first case is actually we are seeing the low income groups. That's all the red color which you see is basically in the first case is actually in the first map is basically giving you the places where the low income housing is most suitable. Other people who is having a lower income, for them these are the places which is suitable. So the suitability is being considered based on the conditions of the land use and as well as the other existing low income residents which is available there. Similarly, we can also have a middle income distribution, so which you see is mostly in the northern part of these cities. And then we are also having a different commercial and high income groups. So this, as you can see, this is basically a city centers with a high income group or the socioeconomically higher income people are living in these regions. And then we are also having a places which is the upcoming commercial hubs which is coming. So you think of this is actually a 10 years old data sets. So based on all these suitability, then we can combine them together to generate what may be the expected class of a particular piece of land that can be assigned to in 2000 or in a near future. So in this case, the future we are talking about the case study of 2013. So we use 2005 and 7 to generate the suitability maps for 2013, and then best suitability map has been composed together to get you the final output map of 2013 in this case. Once we have that map, then we can allow a certain proximity rules to interplay. So that's the basically a part which is, we call it an agent or active agent based modeling techniques. So we look for a kind of how a particular house is being built in. So in that case, generally we can say any household, if a piece of land has to be converted into a particular household, first of all the size of that piece of land has to be good enough to make a house. So based on the different income group, the people will have different sizes of plots, and those plot sizes should be available. That is the first rule. Then second is that we also look for a kind of accessibility. So based on the availability of the drivers, the nearest locations, like in this case the proximity, maybe school or hospitals, can be considered. Then there's also an important factors like what are the other people or others income group living in surrounding areas. So that will have another influence which will be there. And of course then there's an accessibility in terms of transport connections and so on. So these are the few rules which, apart from the suitability, these additional rules will play an important role to allow someone to make houses. So how can we accommodate this section? So it's like telling that you're having a piece of land, but are you going to build a houses on that piece of land depends upon a lot of other external factors. For example, availability of fund, or maybe in the near future, what is your expectation? Are you going to stay in this city, or you'll be going to some other cities? So these kind of different decisions will influence that if a particular land use is going to be converted into another or not. So that's to accommodate these kind of randomness in a development areas. We have to use certain kind of algorithms related to. One of them is basically in the cases related to agent-based modeling that can be used. So this shows the so based on those rules, we can know that how much expected growth rate in a particular years is expected, and considering all those factors in different distributions, then we can allow the different agents to play in a study area, and finally it is going to make a certain choices. So this is just an example where agent-based models is being used to create or say that in the near futures which are places the housing is of a particular income group, based on the income group status is going to come. So finally the overall areas and zone it gets created, and then we do some kind of validations, because we are talking about the last or years or the previous years. So we find it like the basic prediction or actual number of the piece of land falling under the different income group, they are having a very good accuracy, around 80 to 85% of the accuracy was being found out. So this is the use where the land use land cover models, which is built on different machine learning or the statistical based techniques, again get combined with agent based modelings to provide which again can take a decisions based on a simple logic, or it can also work on some complex cases where we can use it. So this particular techniques of establishing a relationship between land use is not only restricted to in 2 dimensions. This can also be used in the 3rd dimension as well, which is nowadays we are seeing, especially in the cases where city growth is mostly now happening in a vertical direction instead of horizontal directions. So this is again, in this case we are taking a study or an area of a particular piece of road in which around surrounding which we expect that there will be and how does these area is going to build up or look into future. So this is again an earlier studies which we had done it in a city areas of Dehradun. So there you see a small piece of land taken from the Google Earth, which we have taken in, and then we have different classifications of that particular areas, so built up and non-built up areas, and we are also having a certain classification of those maps, especially at the level 3. So at level 3 basically we are talking about commercial, non-commercial, or those kind of residential and so on. So those the level 3 classifications we carried out on these data sets, and then we combined it with the distribution of height or the housing distributions, and how does the different land use height distribution is there in surrounding areas. So in this case we have found out that each of the classes, especially in different type of commercials area, will have certain number of floors with for example, let's say if the land use is hotels, then it is 80% of the chances is there that this will be a 2-floor hotels. Similarly, if any kind of showrooms is there, so 50% of the distribution of all the showrooms are basically having a just single floor, that's a ground floor, and around 10% is having the 10% of the total showroom is having a 2-floor, and another 10 to 25% is having more than 2 floors. So those kind of things, 2-floor and correspondingly more than 2 floors. So this distribution of different land use is already available to us, along with the different classes, and then once we generate those suitability map which we have seen earlier. So this is also an example where instead of commercial we can also have residential areas and their distributions. So as we can see that the 1st floor, 2nd floor and 3rd floor, so most likely the residential zone, especially earlier on those maybe 10 years back, the majority or approximately 60% of the housing were having a certain piece of land which was on a plot size different distribution, and as well as the floor distribution is being followed. Again, you see the majority of the residential areas were not more than 1 floor in this study area zone. So once we know what's the floor distribution, what is the average plot size, that we can also find out from the maps, and then we can establish a relationship between the different type of land use. So similarly we can take other types. So we just saw just 2 maps. There are other classes as well, not only residential or commercial, the other land use type and their distribution was also there. Then what we can do is we will like to see that what is the future predictions in, let's say, in the 5 years or 10 years, what kind of growth do you expect in this particular areas. So for that we look into a planning documents which says that what is the expected land use conversions in next as per the current planning scheme, what kind of different plots is being allowed from the government point of view. So that's a part of, as a part of planning documents. And then we can see that in those areas there are not much commercial, especially the educational institute was not being planned in futures, and as well as there's also been no future development of any kind of government areas and zones like that. So means whatever piece of land is now being left will be having some kind of commercial or the residential uses. So in that case, we have to see that which particular piece of land is good enough for a particular cases. Is it the land use is good for commercial zone or commercial areas, or is it good for residential areas? So those kind of things can be given by a suitability maps. And then we'll also look for a kind of basically the expected accommodations of each of those class. So let's say one piece of land is available to us, then we would like to know what is the expected plot size which will be which can be carved out from a piece of land. So that is going to give you the number of plotting size for a residential or as a commercial areas. Then we also look into some of the geometrical aspect of those land. So like, is it a convex or concave, which is again an important aspect for especially in case of making and built up areas. And then we also put some kind of constraint that which piece of land there has to be distances from the road, or it has to be it cannot be a kind of large amount of corners. At maximum piece of land will have 4 or 5 or 6 corners. Those kind of things can be put in as a part of rules. So that's the first rule which we put it. The second is basically a distances, that what are the current policies which says that from a particular road how far which we to build or go for a particular land use, which particular what are the different governing rules. So in this case we see it's basically a distance based rules, like if you're having a road, so there are different norms, like beyond, if you want to build a larger residential areas, there has to be a proximity of 100 meters, multiplexes and so on. So showroom of one sizes, multi-complex and so on. So the specific constraint has been put in. So these constraints are also taken as a part of input rules for future development. And then we look for that what is the current distribution of different land use, and what is the expected, based on that we can say that what is the expected I should say the land use in the futures, based on if we consider the distribution or compositions of different land use to be of similar type. So this particular distribution, then we look into that which particular piece of land is good enough for computing or doing some kind of conversion of one piece of land to another one. So based on that we could find out that there are few places which can be having a particular plot areas, and considering the development constraint which we have seen the earlier distribution of different land use types, we can put those constraints and we can see that a piece of land, it can be available there. So what kind of conversion is possible? So in this case that piece of land can be converted into 4 different pieces, or considering all the different shape wise constraints. And then we can look for a kind of development. So in this case we are seeing that the distance is also 100 meters. So residential buildings and plannings can be done. So accordingly, based on the distributions and suitability maps, the residential areas can be created and that can be built in. So in this case we are showing a future landscape or development in a particular zone. Same way we can have for other plots as well. So we can see that it's a kind of mixed land use where residential zone and as well as commercial zone can be come up. So means that piece of land is good enough to serve both these purposes, and accordingly the future development is expected. So considering the same case for other areas as well, and we can see the different land use, all those four piece of land and how it can be converted into different land use types. So on the basis of that, we were able to tell that, or we were able to predict in which portion or which zone which type of land use is going to be is coming in the near future. So we, in this case, what we do, we take a suitability map along with the proximity rules and then the geometrical constraint rules combined together gives a kind of distribution of future prediction and the landscape of a particular city. And that's how the predictions can be made in a vertical directions as well, and then accordingly the different uses can be used. I mean, the planning we can get a feeling that what's the expected growth in a particular areas, and socioeconomic activities and so on can be linked with such development. So these are the few cases where the different modeling techniques, including machine learning or statistical based modeling techniques, combined together with the agent based and rule based algorithms, can be used for giving you a prediction for near futures, and which can be especially not only in the horizontal but also as well as in the vertical directions. So with this, I'll be closing this session and I'll be having questions after the short while.